Welcome to Talk Tensors. Think about the last time you tried to book a flight online.
Oh, yeah. It's always a nightmare.
Right. I mean, you log on and you're immediately hit with a full screen cookie consent banner. You click accept. You navigate to the search bar, type in your destination, hit enter.
And then the pop-ups start.
Exactly. A pop-up appears asking you to subscribe to a newsletter. You have to hunt for that tiny, practically invisible X just to close it. And then you finally get to the calendar widget, but every single time you click a departure date, the return date just resets itself.
It is entirely a labyrinth of dark patterns and shifting layouts. Sheer friction.
Yeah, exactly. So imagine a world where you just type into a command line, book me a round-trip flight to London for next week under $800, and you just walk away.
You go make a coffee.
And while you're pouring it, an autonomous agent silently navigates that chaotic airline website for you. It dodges the pop-ups, wrestles with the calendar widget, and secures your ticket.
It's the ultimate dream of machine delegation, really.
It is. And on this deep dive, we're looking at the exact architecture that is making that scenario a reality. We are a professional machine learning academic paper summarization deep dive, and today we're exploring a massive breakthrough in the field of generalist web agents.
We're getting into a benchmark data set called Mind2Web and its accompanying agent framework, Mind2Web.
Right. And to be clear, we aren't talking about simple customer service chatbots today. We are talking about autonomous systems designed to follow open-ended natural language instructions.
Systems that execute incredibly complex, multi-step tasks across virtually any website on the open internet.
Okay, let's unpack this, because why is it so incredibly hard to build an AI that can surf the web like a human? If I look at the history of the space, what you could call the dark ages of web agents, it seems like researchers were treating the internet like a controlled laboratory rather than the Wild West it actually is.
That is a highly accurate assessment, yeah. Prior to the architecture we're analyzing today, the training environments for web agents were just heavily sanitized.
Yeah.
The standard practice was to use simplified, simulated sandbox environments.
Like Mind2Web ++or, right?
Yes. The most famous one was likely Mind2Web ++dem.
I remember seeing demonstrations of that. It looked like a website built in 1995 for like a kindergarten computer class.
Precisely. I mean, it consisted of these tiny toy HTML environments. You would have a gray box with a single text field and a button that just said submit.
Right.
Or maybe a highly simplified fake email inbox with exactly 3 messages. And the agent would learn to click the button or type in the box.
Which is fine for proving a concept, I guess.
It was useful for proving that an agent could theoretically interact with HTML, sure, but it stripped away, 99% of the complexity of a real web page?
Yeah, there were no tracking scripts, no CSS hiding elements.
No nested drop-down menus triggered by weird JavaScript hover events. It was just a sterile vacuum.
It's basically like training someone to drive by having them play Mario Kart and then just dropping them into rush hour traffic in Manhattan and saying, good luck.
That's a perfect analogy. And, even when researchers did attempt to use real websites, they severely restricted the agent's scope. There was a highly influential data set called WebShop, for instance.
Oh, I remember WebShop.
It's a massive leap forward at the time, but it was exclusively a simulated e-commerce environment. The agent became exceptionally good at searching for a product, reading the reviews, selecting a color, and clicking the checkout button.
But if you took that exact same WebShop agent and dropped it onto, say, the Virginia DMV website and told it to renew a license,
it would completely collapse. It possessed absolutely no generalized understanding of web navigation. It had essentially overfit to the logic of a digital shopping cart.
Wow.
Furthermore, the way humans had to interact with these older systems was entirely unnatural. You couldn't just give the agent a high-level goal like, check the weather in New York for tomorrow.
Because a high-level goal requires the agent to infer all the intermediate steps itself, right? With those older sandbox-trained models, you essentially had to write a script for them using natural language.
Exactly. You had to say, locate the search input field, type the string New York, locate the button with the label search, execute a click, wait for the network response.
Locate the element with the text tomorrow, execute a click. It's exhausting.
Which completely defeats the purpose of an autonomous agent. I mean, if the human has to meticulously plan every single micro interaction and micromanage the execution, you haven't saved any time or cognitive load at all.
You've just replaced clicking a mouse with typing extremely tedious instructions.
Right. The bottleneck here wasn't necessarily that the core reasoning capabilities of the language models were fundamentally broken. The bottleneck was the interface layer itself, the raw HTML.
Let's drill into that HTML bottleneck, actually, because this is where I think a lot of people's intuition fails. We look at foundational large language models today, models with hundreds of billions of parameters that can write Python scripts or pass the bar exam.
Sure.
So the obvious question for anyone listening is, why can't we just feed the raw HTML code of a web page directly into the prompt, like Neo reading the Matrix? Why can't the AI just read the code, find the line that says button tag book flight, and execute the action?
The intuition fails there because humans vastly underestimate the sheer volume of hidden noise on a modern web page. When you look at an airline website, your visual cortex instantly filters out the noise. You just see a clean layout, a blue button, a white text box.
But the computer doesn't see pixels.
No, it sees the document object model, the DOM. The DOM is a massive, deeply nested tree structure of code. A single visually simple web page today can easily contain well over 2,000 distinct HTML elements.
And most of those elements have absolutely nothing to do with what the user is actually trying to achieve.
Precisely. The vast majority of that code is just infrastructure. It consists of tracking pixels, analytic scripts, endless nested div tags used purely for formatting, hidden SVGs for rendering icons, metadata.
So if you try to dump the entire raw HTML of a site like Expedia into a language model,
you immediately hit the context window limit. You are asking the model to process tens of thousands, sometimes hundreds of thousands of tokens just for a single static view of the page.
But wait, why not just clean it up? Like, why not run a script that strips out all the CSS styling, strips out all the JavaScript, removes the metadata, and just feeds the bare bones text and links into the model? Just give it the skeleton.
You would logically think that's the solution. But in the era of modern single-page applications, frameworks like React, Vue, or Angular, that approach completely breaks down. If you strip the JavaScript from a modern web app, the page literally ceases to exist.
Wait, really?
Yes. If you inspect the raw HTML file sent by the server for a React app, it is often practically empty. It might just be a single line of code that says divide equals root, and that's it.
Oh, because the JavaScript is what actually builds the interface on the fly in the user's browser. It fetches the data, constructs the buttons, renders the text dynamically.
Exactly. The interface is generated dynamically.
Right.
You need the complex code to render the state of the page. You cannot just look at a static text file. Furthermore, the DOM is highly stateful. It mutates constantly based on user interaction.
Right. You hover your mouse over a destinations tab, and suddenly a massive mega menu drops down, injecting like 100 new HTML elements into the DOM tree instantly.
And if you feed a static snapshot of the HTML into an LLM, and the LLM decides to click a drop-down menu, the entire landscape of the page changes. The map the LLM holds in its memory is instantly obsolete.
So you can't just give an AI a static one-time map of a constantly moving target.
No, and expect it to navigate a 10-step sequence successfully. It's impossible. The context window gets overwhelmed. The cost of processing those tokens for every single step becomes wildly prohibitive, and the dynamic nature of the DOM just causes hallucination.
This perfectly frames the wall that researchers hit. You can't train generalist agents in a sterile sandbox because they fail in the real world. But you can't just throw them at the real world because the sheer volume of HTML data crushes their processing capacity.
That was the stalemate.
So to break this, we needed a completely new approach to training data. We needed a way to capture the absolute chaos of the live internet, but structure it in a way that an AI could actually digest. And that leads us directly to the foundation of this research, the Mind2Web dataset.
The sheer scale and ambition of Mind2Web is really what separates it from legacy datasets like WebShop. The researchers understood that to build a generalist agent, you have to expose it to the maximum possible variance in web design.
How big is it?
It contains over 2,000 open-ended tasks. But the critical metric is that these tasks were collected across 137 different real-world websites.
And these are not just 137 different e-commerce stores, right? They span 31 entirely distinct domains. We are talking travel, information, government services, shopping, entertainment, social media.
The domain variance is crucial because it tests the agent's semantic understanding of the world, not just its ability to recognize a shopping cart icon. And they made a very deliberate architectural choice regarding the nature of the tasks. They focused exclusively on high-level human goals.
Let's give some examples to ground this for you listening. The dataset isn't just buy a toaster. It includes incredibly complex multi-stage directives. For instance, one task is find Elon Musk's profile, follow him, turn on notifications, and like his latest tweet.
That's a great example.
Another is book a round-trip flight on July 1st from Mumbai to London for 2 adults, economy class, or schedule a DMV appointment for a commercial vehicle knowledge test in the state of Virginia.
The complexity embedded in those high-level goals is staggering when you actually break it down into machine interactions. I mean, if you tell an agent to book a flight, it must possess a robust internal world model.
It has to know how a flight booking actually works.
Exactly. It needs to know that booking a flight requires locating the origin field, typing a city, waiting for an asynchronous autocomplete dropdown to appear,
Selecting the correct airport code, moving to the destination field.
interacting with a notoriously difficult calendar widget to select a date, finding the passenger dropdown, incrementing the adult count to 2, clicking search, and then finally parsing a complex grid of dynamic prices.
It forces the system to decompose a massive abstract goal into a granular sequence of actionable DOM manipulations on the fly, reacting to the website's layout at every single step.
Precisely. And the methodology they use to collect these human demonstrations is a fascinating study in dataset engineering. They couldn't just write automated Python scripts to generate this data.
Because scripts don't navigate like humans do. Scripts use hard-coded XPaths or element IDs, which completely bypasses the visual and semantic reasoning we were trying to teach the AI in the first place.
Right. They needed genuine human interaction traces, so they utilized crowd workers. They hired human annotators via Amazon Mechanical Turk.
And I do want to highlight a crucial detail here for the deep dive. They paid these annotators an ethical wage of $10.10 an hour, ensuring they met local minimum wage guidelines. That is an important standard in an industry that often relies on heavily underpaid ghost work.
It's very important. But using human annotators introduces a creativity problem. If you ask a crowd worker to come up with a task on a travel website, they will inevitably default to the most obvious repetitive tasks.
Yeah, they'll just search for a flight to New York 50 times in a row because it's the fastest way to complete the job and get paid.
Which would result in a data set with 0 variance. So the researchers employed a brilliant workaround. They utilized ChatGPT to generate 50 distinct seed tasks for every single website.
Oh, that's smart.
They essentially asked the model, what are 50 wild, complex, interesting things a human might try to do on the DMV website?
And here is the clever part. They showed these seed tasks to the human annotators solely for inspiration, but explicitly forbade them from copying the tasks verbatim.
It's a psychological primer. You use the AI's vast generative space to prime the human pump, forcing the human out of their repetitive rut.
But you still rely entirely on the human's genuine real-time intuition to actually map out the interaction trace on the live website.
It ensures semantic diversity in the data set while maintaining the grounding of real human navigation. But this methodology introduces what is arguably the most severe software engineering challenge in agentic AI research.
The real-world consequences.
Exactly. If you are hiring humans to demonstrate how to book a real flight on United Airlines, or how to schedule a real appointment on a government server, or how to buy real stocks on a brokerage site, how do you record that data without executing real-world consequences?
Right. If the task is buy 100 shares of Apple, you can't have a mechanical Turk worker actually draining thousands of dollars from a bank account just to record the mouse clicks.
And you cannot clog up the live Virginia DMV scheduling system with thousands of fake appointments, because that crosses the line into a denial of service attack. You would be degrading critical public infrastructure.
So how did they solve it? This is where they introduced a critical safety innovation during the demonstration phase. They built a specialized recording browser for the annotators, and within that browser, they implemented an operation called clickfake.
The mechanism of the fake click is elegant. When an annotator is navigating the live site, they act entirely normally for the intermediate steps. They click the search bars, they type the text, they navigate the menus.
But when they reach the final terminal action, the point of no return, like the confirm purchase button or the submit application button,
they don't execute a standard mouse click. They select the element and trigger the click fake command.
Wait, if they trigger a fake click, how does the system know they actually targeted the correct element?
Because the recording browser intercepts the interaction at the DOM event listener level. It records the human's explicit intention. It logs the exact X path of the button, the surrounding HTML context, and the semantic intent of the action.
But the browser intentionally suppresses the network request.
Yes. It intercepts the HTTP POCUS request before it ever leaves the human's computer, preventing the state-changing side effect from reaching the live website's server.
It's basically the software equivalent of a firing pin's safety on a weapon. You can pull the trigger, the hammer drops, the system records that a perfect shot was lined up, but the firing pin never actually strikes the primer. The missile doesn't launch.
That is exactly the mechanism. And the implications of this for reinforcement learning and AI safety are profound. Historically, the bottleneck for training AI in grounded environments has been the cost of failure.
Because if an AI makes a mistake in a simulated video game, it just loses points.
But if an autonomous agent makes a mistake on a live banking website, it commits financial fraud. The fake click operation allows researchers to build massive data sets of high-stakes terminal actions entirely safely. It decouples the learning of the interaction logic from the execution of the real-world consequence.
It's a massive leap forward. So through this painstaking process, combining AI-generated seed tasks, human intuition, live website navigation, and the safety valve of the fake click, the researchers assembled Mind2Web.
They now possess this incredibly rich, diverse data set of human interaction traces across the wildest corners of the internet.
But the core problem still remains. We have the data, but we still have the HTML context window bottleneck. You still can't just feed the entire DOM tree of these sites into a language model to train it.
Which necessitates the creation of an entirely new cognitive architecture for the agent. This is where the researchers developed the MindAct framework.
Here's where it gets really interesting. MindAct is not just a model. It is a highly specialized pipeline designed specifically to solve the information retrieval problem inherent in raw HTML.
This is the brain of the operation. And what I find so compelling about MindAct is that it doesn't try to solve the problem with brute force. It doesn't try to build a massive trillion parameter model that can swallow a whole web page at once.
Right.
Instead, it uses a two-stage architecture. It fundamentally separates the cognitive process into two distinct tasks. Where should I look? And what should I do?
This division of labor is mathematically and computationally necessary. Let's examine stage one, which functions as the candidate generation phase. I like to think of stage one as the bouncer.
A bouncer, like that.
Yeah, instead of forcing the giant large language model, the CEO of the operation, to read through thousands of lines of bloated, irrelevant web page code, MindAct deploys a highly specialized, fine-tuned small language model to stand at the door and check IDs.
In this research, they utilized a DiBerta model with roughly 86 million parameters.
Which, by today's standards, an 86 million parameter model is microscopic.
It is highly efficient, has a very low memory footprint, and can run inference almost instantaneously.
So how exactly does this microscopic model process a massive web page?
DiBerta operates in this pipeline as a cross-encoder. It does not try to understand the entire page holistically. Instead, it systematically evaluates every single interactable element in the DOM tree in isolation.
Okay, so it takes the user's high-level task description, for example, book a flight to London.
And it pairs that text with the isolated text representation of an individual HTML element. It looks at the element's tag, its textual content, and its attributes like class equals btn primary, area label equals submit search.
So it's looking at the raw code of just that one button.
Yes. The cross-encoder concatenates the task query and the element snippet. It feeds them together through its transformer layers, allowing the attention mechanisms to deeply analyze the semantic relationship between the words in the user's goal and the specific attributes of the HTML code.
And then it scores it.
It outputs a matching score between 0 and 1. A score of 0.99 means this element is highly relevant to booking a flight. A score of 0.01 means this element is a hidden tracking pixel that should be ignored.
And because DiBerta is so small and efficient, it can run this mathematical scoring process across thousands of individual elements on a single web page in milliseconds. It scores the buttons, it scores the text boxes, it scores the hidden links.
And then it simply ranks them. It takes the top 50 highest scoring elements and discards the rest.
It acts as an aggressive semantic pruning mechanism. It takes a DOM tree containing 2,000 elements, strips away the 95% of the page that is structural noise or irrelevant content, and isolates a clean, manageable list of 50 candidate elements that actually matter for the current task.
It is exactly like an executive assistant meticulously filtering a chaotic, overflowing inbox down to the 50 most urgent emails so the CEO can actually focus on decision-making rather than sorting spam.
I love that analogy. So once the bouncer has cleared the noise, the pipeline moves to stage 2, the executive. This is where the heavy lifting occurs.
The pruned list of 50 candidate elements is handed over to a large language model. In the core experiments, the researchers relied heavily on models like FLAN-T5, specifically the 3 billion parameter version, though they also experimented extensively with off-the-shelf models like GPT-4.
And here is where we encounter what I believe is the most elegant design choice in the entire Mendeley architecture. It's not just about the model they used, it's about the prompting strategy. It's how they asked the model to make a decision.
The researchers faced a critical fork in the road regarding how to extract the final action from the LLM. The standard intuitive approach in natural language processing is direct generation.
Meaning you feed the model the pruned HTML and the task, and you prompt it to generate the correct string of code. You ask it to output the exact ID or XPath of the element it wants to click.
Which sounds reasonable, right? You ask it a question, it writes out the answer. I want to click the element with id equals submit btn 452.
So why didn't they do that?
Because direct generation in a rigid syntactic environment like HTML is incredibly brittle. We have to remember how autoregressive language models actually function under the hood. They do not output whole sentences at once. They predict the next token in a sequence based on a probability distribution.
Okay, so if the target element idea is check out BTN final step 3.
The model has to correctly predict every single token in that string in perfect sequence. If it hallucinates a single character, if it predicts step 2 instead of step 3, because step 2 appeared more frequently in its pre-training data, the entire action fails catastrophically.
Wow. The web browser will look for step 2, it won't exist, and the agent just crashes. A single hallucinated digit ruins the entire multi-step plan. So how did Mingdact avoid the generation trap?
They converted the action prediction problem into a multiple choice question answering format.
Oh, wow.
It's a brilliant reframing of the task. They took the top 50 candidate elements provided by Deberta and clustered them into small groups of 5. They then constructed a prompt that looks exactly like a standardized test.
So the LLM is given the task, the history of its previous actions, and a prompt that essentially reads, based on the goal, which of the following elements should be interacted with next? A element 1, B element 2, C element 3, D element 4, E element 5, or F, none of the above.
That is exactly it. So instead of asking the model to blindly generate a string of code out of thin air, it just has to output a single letter.
That is fascinating.
If the LLM analyzes the first cluster of 5 elements and determines that none of them are the correct submit button, it outputs the token for none of the above. The system registers that choice, discards the cluster, and feeds the LLM the next group of 5 elements from the top 50 list.
And it just iterates through the clusters until the model spots the correct element. Say it looks at cluster 3, sees the submit button as option C, and outputs the letter C.
Once it narrows down the target, it then predicts the operation like click, type, or select, and if the operation is type, only then does it output the specific text string it needs to input, like New York.
The reason this multiple choice design is so profound is that it perfectly aligns with the fundamental strengths and weaknesses of large language models.
Across the entire field of machine learning, we see a consistent trend. LLMs are vastly superior at discriminating between provided options than they are at generating exact, highly specific stream matches from scratch.
Because by forcing it into a multiple choice structure, you are constraining the model's output space. The probability mass is focused entirely on just 6 possible tokens, A, B, C, D, E, or none.
It doesn't have the opportunity to hallucinate an invalid HTML tag because it isn't generating HTML. It's just picking from a pre-validated menu.
It structurally eliminates an entire class of syntax errors. Every option provided to the model in the multiple choice list is guaranteed to be a real, existable, interactable element currently rendered on the page because it was pulled directly from the live DOM by the stage 1 bouncer.
It forces the LLM's semantic reasoning to remain strictly grounded in the physical reality of the website interface.
Okay, so let's summarize where we are for you listeners. We have Mind2Web, this massive, realistic, human-demonstrated data set capturing the chaos of the open internet. We have Mingdact, this highly efficient 2-stage architecture that solves the context window problem using a Deberta bouncer and solves the hallucination problem using a multiple-choice executive LLM.
The theoretical foundation is incredibly sound.
It is, But the obvious next question is, did it actually work? When they turned this pipeline on and pointed it at the live internet, could it actually surf the web?
To answer that, we must examine the evaluation framework the researchers designed. And I must credit them here. The evaluation was remarkably rigorous.
They didn't just test the agent on tasks it had seen, right?
No, they constructed a generalization crucible, dividing the testing into 3 distinct levels of increasing difficulty.
Walk us through the 3 levels of the crucible. What exactly is the agent facing?
Level 1 is cross-task. In this scenario, the agent is tested on entirely new tasks, but on websites it is encountered before during training.
Okay, so for example, during the training phase, the agent might have processed thousands of examples of humans searching for flights on United Airlines. It knows the layout of United.com.
Exactly. In the cross-task evaluation, it is asked to execute a novel task on that same site, such as checking the status of a specific flight number or navigating to the baggage policy page.
Okay, that makes sense. It tests its ability to adapt to new semantic goals within a familiar physical environment. What is level 2?
Level 2 escalates to cross-website. Here, the agent is tested on entirely unseen websites, but within familiar, broad domains. Returning to the travel example, the agent was trained extensively on United Airlines and Expedia. It understands the conceptual domain of travel booking.
But in the evaluation,
it is dropped onto the homepage of Delta Airlines, a site it has never seen, with a completely different layout, different CSS frameworks, and different menu structures, and told to book a flight.
That makes perfect sense. It tests whether the agent has learned the abstract concept of a calendar widget, or if it just memorized the specific pixel location of United's calendar. And what is the final level?
Level 3 is the ultimate test of general intelligence cross-domain. The agent is tested on entirely unseen domains that have no semantic overlap with its training data.
Like going from shopping to government portals.
Exactly. Imagine an agent that was trained exclusively on e-commerce shopping carts and social media platforms. It knows how to add shoes to a cart and like a photo. In the cross-domain evaluation, it is abruptly placed into a government portal and instructed to schedule a commercial driving test at the DMV.
Or placed into a specialized software dashboard and asked to configure a server firewall.
It has never seen the websites, and it has never encountered the semantic concepts underlying the tasks.
That is a brutal test. So what were the numbers? How did the Mandak framework perform when subjected to this crucible?
The results were highly illuminating, both in their successes and their failures. The best fine-tuned model, which was the Mind2Web pipeline, utilizing the 3 billion parameter FLAN T5XL as the stage 2 executive, achieved an approximately 52% step success rate on the familiar websites in the cross-task level.
Okay, I need to pause here and provide some context because out in the real world, someone hears 52% and immediately thinks, that's an F on a math test. That's terrible. It flips a coin and fails half the time. But we have to understand how brutally unforgiving the step success metric actually is in this benchmark.
It is a zero-tolerance metric.
Exactly. For a single step to be marked as a success, the agent must select the exact right element out of thousands of candidates. It must choose the exact correct operation, click, type, or select. And if it is typing, it must generate the exact correct text string.
Any deviation is a failure.
If the agent perfectly identifies the deeply hidden passenger drop-down menu, perfectly selects the type operation, but inputs the word to instead of the number 2, the entire step is marked as a failure. And a full task like booking a flight typically requires a sequence of 10 to 15 perfect consecutive steps.
So achieving 52% step accuracy in the wildly unpredictable environment of the live internet is actually a massive baseline achievement.
Right.
It demonstrates that the architecture functions. However, as expected, performance degraded significantly as the difficulty increased. When the agent moved to level 2, the unseen websites in the cross-website evaluation, the step success rate dropped from 52% down to approximately 39%.
Which is entirely intuitive.
Yeah.
You switch from the sleek UI of United to the clunky UI of a regional airline, the CSS classes change, the DOM structure is deeply nested in archaic tables, and the bouncer model struggles to isolate the correct candidate elements. But this brings us to what I consider the absolute aha moment of the entire data set. Look at the performance for level 3, the entirely unseen domains.
This is where the data reveals a profound insight. The performance on the cross-domain level was nearly identical to the performance on the cross-website level. It hovered right around that exact same 39% mark.
Wow. Let that sink in for a second. The agent performed just as well on a government DMV portal it had never seen, concerning a topic it had never studied, as it did on a new airline website when it was already an expert in travel.
If we connect this to the bigger picture of AI development, this statistical parity pinpoints the exact location of the current bottleneck in agentic AI. The data unequivocally proves that the AI does not struggle with domain knowledge.
Because foundational LLMs are pre-trained on terabytes of human text encompassing the entirety of the internet.
Yes, the model already possesses a latent conceptual understanding of how a DMV scheduling system ought to function, or how a mortgage calculator works. It understands the underlying logic of the human world.
Right. The semantic goal is easy. What it struggled with is the bizarre, unpredictable, deeply idiosyncratic visual and structural design of individual websites. The human interface layer is the friction point.
The AI isn't failing to book the DMV appointment because it doesn't know what a driver's license is, or because it doesn't understand the concept of time slots.
It's failing because the Virginia DMV website hides the critical next button inside a deeply nested, invisible table structure built in 2004, and the agent's parsing logic just gets lost in the DOM.
The structural interaction logic, the actual mapping of semantic intent to poorly written HTML implementation, is the real barrier to autonomy.
So we know the fine-tuned 3 billion parameter FLAN T5 model hit a ceiling around 39% on unseen sites. But the researchers didn't stop there. They conducted a battle of the models, pitting their fine-tuned specialized model against the massive off-the-shelf commercial titans like GPT 3.5 and GPT 4.
And they didn't fine-tune the commercial models. They just used three-shot in-context learning.
They basically just showed the models 3 examples in the prompt and said, go figure it out.
And the divergence in performance between the commercial models is highly instructive regarding the evolution of reasoning capabilities. GPT-4 performed spectacularly. With just 3 examples in the prompt, acting entirely in a few-shot capacity, it essentially matched the performance of the extensively fine-tuned FLAN T5 XL models on unseen websites.
It consistently hit that 36% to 37% success rate in unseen environments. That is staggering. GPT-4 essentially walks in off the street, glances at 3 flashcards, and ties the score of a specialized model that spent weeks studying the entire Mind2Web curriculum.
It demonstrates the incredible zero-shot generalization capabilities embedded within GPT-4's massive parameter count. Okay. But the performance of its predecessor, GPT 3.5, offers a stark contrast. GPT 3.5 failed miserably across the board. It only achieved roughly a 20% accuracy rate.
And the reason GPT 3.5 failed is my absolute favorite behavioral insight in this entire paper, because it highlights a flaw that is so deeply recognizable in human cognition. It failed almost entirely because of the none of the above problem.
Let's unpack the mechanics of that failure. Recall the multiple choice prompting strategy. The model must choose A, B, C, D, E, or none of the above. What the researchers observed in the interaction traces was a persistent behavioral loop in GPT 3.5. It simply could not grasp the concept of long-term, multi-step planning in a latent space.
Here's how I visualize it. It's exactly like a teenager looking in the refrigerator for ketchup. If the ketchup bottle isn't sitting right in the front row, immediately visible the second the door opens, the teenager just stares at the open fridge, sighs, and yells, "We're out of ketchup."
They completely lack the multi-step planning required to think, the ketchup might be behind the milk. I need to physically move the milk, creating a new state in the fridge to reveal the hidden ketchup.
That analogy perfectly maps to the model's behavior. If the final goal of the task, for instance, click the like button on Elon Musk's pinned tweet, was not immediately visible in the DOM elements on the very first page the agent looked at, GPT 3.5 would analyze the candidates, realize the like button wasn't there, and stubbornly output none of the above.
And it would do this repeatedly, trapped in an infinite loop of indecision.
It couldn't realize that it needed to execute intermediate preparatory steps. It couldn't reason, I don't see the tweet, therefore I need to click the search bar, then I need to type Elon, then I need to hit enter, then I need to click his profile picture, then the like button will appear.
GPT 3.5 lacked the cognitive horizon to plan a sequence of actions toward a delayed reward. It just gave up at the first hurdle.
It lacked a robust internal world model of web navigation. GPT-4, conversely, possessed that extended planning horizon. It could maintain the final goal in its context while independently deducing and executing the necessary intermediate navigational steps, even when the final target element was entirely obscured from its current view.
So if you're listening to this and wondering how this applies to the AI tools you use or build every day, this is the core takeaway. Raw computational intelligence is necessary, but it is not sufficient.
If you are building agentic systems, you cannot simply plug an LLM into a web browser API and expect it to automate your workflow. Without rigorous architectural guardrails like breaking the chaotic DOM down into manageable chunks, forcing a multiple-choice selection to prevent syntax hallucinations, and utilizing models capable of long-horizon planning, your agent will fail.
It will devolve into a frustrating, looping gimmick. You need a structured framework.
However, to maintain intellectual rigor, we must also examine the blind spots of the Mind2Web framework. The authors of the paper are commendably transparent about the limitations of their current approach, and these limitations point directly to the future frontiers of the field.
Let's play devil's advocate. Where does this architecture break down when it hits the messy reality of the modern web?
The most glaring limitation, and the most difficult to solve computationally, is visual blindness. Mind2Web operates entirely, 100%, on the textual HTML DOM tree. It parses code. It does not actually see the rendered visual web page the way a human visual cortex does.
It's essentially reading the sheet music of a symphony, but it is deaf to the actual music being played. It knows the notes, but it doesn't know what it sounds like in the room.
That is an apt metaphor. The model can read an HTML tag that says button tag submit, but it has absolutely no idea if that button is rendered as bright, flashing neon red, taking up half the screen, or if it is rendered as tiny, invisible white text on a white background hidden in the footer.
Or, more catastrophically, it doesn't know if that critical submit button is currently being visually obstructed by a massive opaque cookie consent pop-up banner.
Precisely. In the modern web, layout, spatial positioning, and CSS properties like the z-index, which determines the stacking order of overlapping elements on the z-axis, contain crucial semantic information.
If a pop-up has a higher z-index than the input field, a human knows they must close the pop-up first. The Mind2Web agent, operating purely on the flat text of the DOM, might try to click the input field, and the browser will reject the action because the element is visually obstructed.
Operating purely on text is a massive limitation for highly visual, complex single-page applications. Multimodal integration, combining DOM parsing with actual computer vision and screenshot analysis, is the mandatory next step for robust agents.
The agent is basically flying entirely on instruments without looking out the windshield.
Right. What is the next major bottleneck in the research?
The offline cache trap. This is a subtle but critical issue related to how we evaluate agents. To keep the benchmarking fair, reproducible, and scientifically rigorous, the researchers evaluated the Mind2Web agents on cached, offline versions of the websites.
They essentially recorded the network traffic during the human demonstration and played it back for the AI.
You have to do this, because you don't want the live Expedia website changing its layout halfway through a benchmark run, which would skew the results and make comparisons between models impossible.
It makes perfect sense for maintaining a controlled scientific variable. But it's terrible for replicating reality.
Exactly. The real web is highly redundant. There are multiple valid paths to the same goal. Imagine you are booking a flight. You might use the interactive calendar widget to select your departure date, or you might just click the text box and manually type 1024-2026.
Both actions achieve the exact same state on the live website.
But consider the offline evaluation environment. If the human annotator used the calendar widget during data collection, the offline cache only saved the specific HTTP network requests and responses associated with that widget.
Oh, I see where this is going. What happens if the agent during evaluation decides to be smart and just manually types the date into the text box instead?
The offline cache completely breaks. The agent's action triggers a network request that the cache has never seen and did not record. The environment throws a 404 error, or simply fails to update the DOM.
The agent executed a perfectly valid, logical action that would have succeeded on the live internet, but the brittle offline evaluation environment failed it.
Which means the 39% success rate on unseen domains might actually be artificially low. The agents might be performing perfectly valid alternative paths, but getting penalized by the limitations of the cached simulation.
Or, conversely, they might fail in entirely novel, catastrophic ways on live servers that the cache currently protects them from. The field desperately needs better, safer methodologies for evaluating autonomous agents dynamically online.
And that ties directly into a third limitation regarding human-computer interaction: the paradigm of one-shot instructions. The way the Mind2Web web benchmark is structured, the user issues a single command at the very beginning, book me a flight to London under $800, and then the human completely exits the loop.
The agent runs blindly forward. But in the real world, complex tasks require a continuous feedback loop. If I tell my AI assistant to book a flight, and it navigates to the checkout page and discovers the price has suddenly surged to $1,200, I do not want the agent to blindly execute the purchase.
You require an agent capable of active clarification. The agent needs the architectural capacity to pause its execution loop, ping the user, explain the discrepancy, and ask for updated parameters.
Yeah.
It must shift from being a blind executor to a conversational collaborator.
Absolutely. Which brings us to the final and perhaps most pressing issue hovering over this entire field of research. We are building systems explicitly designed to seamlessly navigate the web, imitating human interaction patterns to autonomously achieve complex goals at machine speed.
You're referring to the security implications and the escalating arms race with CAP-TTHS.
Exactly. The entire cybersecurity apparatus of the modern web, every CAP-TCHA, every Cloudflare waiting room, every behavioral biometric tracker is designed specifically to stop exactly what Mind2Web is trying to do. If an agent is sophisticated enough to autonomously navigate a complex airline checkout process to buy a ticket for you, that exact same agent can be weaponized.
The dual-use nature of the technology is undeniable. An agent capable of following a user on Twitter can be scaled into a million-node botnet capable of manipulating social consensus.
An agent capable of buying a concert ticket can be deployed to systematically bypass queues and scalp inventory in milliseconds.
If an agent can execute a legitimate financial transfer, it can execute an unauthorized one if it gains access to session cookies.
Cybersecurity paradigms are going to have to evolve concurrently and drastically alongside agentic AI. We're moving past the point where we can ask a user to click all the squares with a traffic light. Multimodal agents will solve those visually in a fraction of a second. The cat and mouse game between bot detection and bot generation is about to escalate into a fundamentally different domain of behavioral analysis.
It is a profound shift in web security. Definitely.
Okay, we have covered the historical context, the brilliant architecture of Mind2Web, the fascinating results of the evaluation crucible, and the structural limitations of the approach. It is time to transition to our signature segment. Welcome to Novel Notions. This is the segment of the deep dive where we take the core findings of the research we just discussed and extrapolate them outward to their absolute, logical, and sometimes wildly disruptive extremes.
And we must explicitly state for the record the following ideas are entirely speculative. They are thought experiments designed for entertainment purposes, intended to test the outer boundaries of the technology discussed today.
Exactly. We are leaving the strict confines of the benchmark and entering the realm of hypothetical architectures. Let's begin with novel notion number 1. I call this the UI-agnostic headless web browser.
Let us lay out the premise for this architecture. What is the fundamental problem it solves?
It is entirely based on the profound aha moment we discovered in the data regarding the cross-domain evaluation. The paper proved that AI models understand high-level semantic domain concepts perfectly. They know what a shopping cart is. They know how a calendar works. What they struggle with, the primary cause of the 61% failure rate, is the visual, idiosyncratic, often terrible UI design of individual websites.
The human interface is the friction.
So what if the future of the internet isn't about building smarter agents that try to navigate our messy websites? What if the future is agents that fundamentally destroy the websites entirely?
Destroy the interface layer, you mean? To decouple the semantic data from the visual presentation.
Exactly. The mechanism works like this. You build a highly advanced local Mind2Web proxy. This agent lives natively on your device, your phone, your laptop, or your augmented reality glasses. It sits directly between you and the internet. When you want to buy tickets to a concert, you do not open Chrome and navigate to Ticketmaster.com. You don't subject yourself to their chaotic HTML, their flashing CSS countdown timers, or their manipulative dark patterns.
Instead, you issue a natural language command to your local proxy.
Right. You say, get me 2 tickets to the concert in the lower bowl. In the background, invisible to you, your Mind2Web proxy establishes a connection with the ticketing server. It parses the site's raw DOM tree. It uses the stage 1 bouncer and the stage 2 executive to locate the necessary endpoints and execute the transaction.
It acts as an aggressive real-time translator.
It standardizes the entire chaotic web into a single uniform interface personalized strictly for you.
If we connect this to the broader evolution of the internet, it functions as the ultimate ad blocker. But it strips away far more than just advertisements. It strips away the entire persuasive design layer of capitalism. Websites cease to exist as visual branded destinations. They are reduced to purely functional API endpoints, queried and manipulated solely by your personal AI proxy.
Yes, you never see a pop-up again, you never see a newsletter subscription form, you never experience a confusing navigation menu. The visual web becomes completely obsolete for utility tasks. You interact with the internet purely through a conversational interface or a standardized minimalist dashboard generated on the fly by your local model.
The economic and structural implications for the technology industry would be catastrophic. If the primary consumer of web content is no longer a human eye, but an LLM proxy parsing the DOM, the entire discipline of front-end web development changes overnight.
Why bother writing complex CSS animations?
Why hire UI/UX designers to optimize button placements for conversion rates? You wouldn't. You would solely optimize your HTML structure for maximum semantic machine readability. Search engine optimization, SEO, would be entirely replaced by AI optimization. The internet would revert to a hyper-efficient, purely utilitarian database.
It's a fascinating, slightly dystopian scenario where the colorful, chaotic web we know just vanishes behind a layer of AI abstraction. Okay, let's move to novel notion number 2. I call this one shadow web reinforcement learning.
This concept directly addresses the offline cache trap and the limitations of the click-fake safety valve we discussed earlier.
Right. The core problem of training advanced agents is the cost of real-world iteration. How do you train an agent to execute thousands of complex, state-changing actions like day trading stocks, managing a corporate cloud infrastructure, or buying real estate without it bankrupting you during the trial and error phase of reinforcement learning?
You cannot let an untrained AI loose on a live brokerage account.
And as we established, if you rely solely on the click-fake interception, the training session effectively terminates at that point. Because the network request is suppressed, the live server never updates the page, the agent never gets to see the confirmation screen.
It never learns what happens after the terminal action, which severely limits its ability to learn complex, multi-step recovery behaviors.
So here's the theoretical mechanism for the shadow web. We take the Mind2Web framework, but we do not just attach it to a large language model. We attach it to a highly advanced generative world model specifically, a model trained to generate dynamic HTML and visual states based on user actions.
A simulated environment generator.
Exactly. When the agent is exploring a live website and decides to use the click-fake operation, say it clicks buy 100 shares of Apple, the local browser intercepts the click as usual. But instead of the session ending, the generative world model instantly takes over.
It looks at the action the agent just took, looks at the current DOM, and it hallucinates the next plausible web page.
What is fascinating here is the architectural shift. You are essentially trapping the agent in a hyper-realistic, computationally generated simulation of the internet.
Yes. It is the matrix, but built specifically to train AI agents. The agent clicks buy. The real internet connection is severed. But the generative model instantly constructs and renders a completely fake but structurally perfect banking confirmation page, complete with updated portfolio balances, transaction IDs, and a success message.
The agent parses this hallucinated DOM, registers that its action was successful, receives its internal reward signal, and continues operating. It is navigating a continuously generated dream state internet.
The utility of this architecture for reinforcement learning is immense. It allows the agent to learn complex, multi-step planning over incredibly long time horizons. More importantly, it allows the agent to safely experience and recover from failure.
If it clicks the wrong button in the simulation and hallucinates a massive red error page or a drained bank account,
it has to learn how to navigate back, undo the action, or troubleshoot the error, all entirely detached from live, vulnerable servers.
It could play out millions of lifetimes of web browsing, making every catastrophic financial and navigational mistake possible in a single afternoon, completely safely confined to the shadow web. By the time you connect it to your real bank account, it has already experienced every edge case the internet has to offer.
It is a highly compelling architecture that theoretically solves the safety bottleneck of scaling reinforcement learning in grounded, high-stakes web environments.
So we will leave you, the listener, with a final lingering thought to ponder as you go about your day and interact with the digital world. If these architectures continue to scale, if frameworks like Mind2Web evolve to the point where autonomous agents become the primary consumers of web content, rather than human beings, what happens to the visual internet?
It's a great question.
If AI proxies are the entities actually parsing the HTML, navigating the DOM, and executing the transactions, will the internet of tomorrow even be designed for human eyes anymore? Or will the sprawling, colorful, visual web we know today slowly atrophy, evolving into a purely structural, machine-to-machine database, leaving human-readable websites as a quaint, inefficient relic of the past?
It forces us to reconsider the fundamental ontology of the web. Is it primarily a visual medium for human consumption? Or is it, at its core, a structured information database awaiting an intelligence capable of parsing it efficiently?
Imagine never manually navigating a clunky, frustrating website ever again. We might just get exactly what we are wishing for, but the internet we get in return might be an entirely unrecognizable landscape. Thank you for joining us on this deep dive. Until next time.